Alrighty. So now that we did the icebreaker, I'm going to let you guys ask me any questions or anything about past material. And then we're going to go through the chapter 17 handout, and we're going to do 4 more questions, 4 or 5, I believe. Should be pretty quick. And then we're going to start chapter 18. I just put tautomerization on here, but we might get a little bit further. We'll just kind of see how it goes. Today we're just going to finish up the handout practice questions, but I'm working on making like a packet for you guys with Dr. West practice problems and some other practice problems for 17 and 18, so we can start doing exam-like problems as well. We're just not going to be able to start that until either Wednesday or next Monday. Also, reminder, we will have SI and tutoring today and Wednesday, but Friday we will not because it's Thanksgiving. And someone asked, is 18 and 19 the last SI sheet? Yes, it is! So we're so close to being done. I'm going to miss you guys, but I'm sure you guys are not going to miss chemistry. So that's so valid. And then someone asked, how should we be studying for 17 and 18? Because there's only like 17 questions in the chapter problems. I know, it's really frustrating because there aren't that many practice problems for you guys to do. So like Katrina and I, actually, we both did it. For the last exam, we put together the like big packet of problems and then we covered it with you guys. We just have to email Dr. West and make sure everything's still fine and dandy. Make sure we're kind of on the right track with the type of problems we're using. Make sure we're not like missing anything, things like that. And then once we have all that checked out, we'll be doing problems like that with you guys as well. Probably not going to email out the packet like last time, but we'll post videos of us doing it like we did for the last exam. I feel like I rambled a little bit, but hopefully that makes sense. And someone said it was super helpful. I'm so glad. I couldn't tell if it was actually helpful or if it was just kind of a mess, but I'm glad you guys found it helpful. Okay, so before we go into the handout, okay, awesome. So someone said, do we have SI on Friday? We do not. I believe campus and everything, like classes, all that kind of stuff, are canceled Thursday, Friday, and they open back up on Monday. Any other questions? Oh, also, the what to study guide thing that I told you guys I was going to send you, I will be sending it to you either tonight or Wednesday night. I didn't want to send it to you before we started chapter 18 for obvious reasons. I didn't want you guys to get overwhelmed or confused. But now that we're going to cover that, I will be sending that out soon. Cool? Any other questions, comments, concerns? Okay, so let's hop right in. And then as always, you guys can ask questions throughout the session as you have them. But we're just going to go ahead and get started. So for the first one, for making and breaking lactones, we are going to... Oh, sorry. Before I start that, someone had a really good point. I was going to cover it at the end of this session, but I'll just mention it now if anyone has to leave early. So FAU does something called Up Owl Night, which is an event hosted by the class office where I work. They run all the tutoring and SI stuff that you guys have. And they basically have a day where from noon to like 10 p.m., they organize all of the SI leaders and tutors to have like final exam review time. And so since I'm an SI leader, I will be having 2 hours of review and 1 hour of tutoring on that day. My hours for the review session, like the big final exam review, will be from 3 to 5 p.m. And this is on December 9th. And I will send you guys an email about that this afternoon as well. So Wednesday, December 9th from 3 to 5 p.m. will be my review session. I'm not 100% sure when Katrina's is or when Jared's is because I spaced out and I forgot. But I will include everyone's hours in the email. Jared just said in the chat, or he's typing in the chat everyone's hours. So thank you very much, Jared. Katrina and I aren't 100% done with our plan and our outline, but essentially we're planning to split the semester in half, and she will do half of the chapters and I will do half of the chapters, just so we're not flying through material and spending 10 minutes on each chapter, because I know that's not very helpful. So yes, we also will be making a little final exam review handout so you guys can go along with us. As always, they will be recorded and they will be posted. They will be kind of long, so it might take 24 hours-ish, but it will be up for you guys. And the link will be sent out to you guys as well, to everyone's sessions. But for now, I have created my Up All Night session, and it's already in Canvas, so you can find it through my Canvas page. I think I covered all the bases. Any questions? Again, I will cover this again in an email and then on Wednesday before the session. Questions, comments, concerns? Thank you for bringing that up. I forgot who it was. So someone asked, is that going to be an exam review or just reviewing material? So I think I understand what you're asking. It's essentially going to be just like all of our other exam reviews. So we're going to spend the first hour-ish going over concepts, and it's going to be like our other exam reviews, but obviously a lot faster because we're going through a lot more chapters. So we're mostly going to focus on key concepts, big concepts. We might not touch on everything, but we're going to cover all the big concepts, and then we're going to spend the second hour going over exam-like practice problems. And if I didn't answer your question, let me know. Okay, cool. Someone asked, when is it? It is Wednesday, December 9th, from 3 to 5 p.m. is my session. Katrina's session is going to be 7 to 9 p.m. And Jared's session is going to be from 5 to 7. So someone else asked, will it be the final exam review or will we have an additional review? We are not 100% sure about this yet. Katrina and I talked about possibly having another review, but I'm not going to tell you guys anything until we've discussed it because I don't want to say anything without talking to her. But we will have that sorted out very soon because I know the exam is coming up pretty soon. Any other questions? Again, thank you to the person who reminded me. Okay, cool. So let's put our brains back in chapter 17. I don't know about you guys, but it kind of feels like forever ago since we did it. But now we have this molecule and we have our reagent. So we have NaH. What kind of reagent is this? What's going to be our nucleophile? Ooh, cool. Someone caught me before I could even do my trick. Yes, the nucleophile is actually going to be the OH. So what is this guy here for? What is his purpose in the reaction? To deprotonate, exactly. Okay, so what kind of charge does this have? Negative. Sweet. So we know Na is positive. And we know that means that the hydrogen must be negative. And so what you guys were saying, it has to deprotonate. Someone said it has to make the nucleophile more nucleophilic. All perfect answers. So it is going to act as a base, steal that hydrogen, give those electrons back to the oxygen. And we are going to get O minus. So now that we have O minus, it is going to act as the nucleophile. It will attack the carbonyl carbon. And so if we have the nucleophile on the same chain as the electrophile, what is going to happen? You're going to form a ring. Awesome. Another way we can say that is we're going to cyclize it, or we're going to make a cyclic compound. All of those are equally correct. So you guys already know what I'm going to say. The big important thing here is to count our carbons. So we know that oxygen is going to be inside the ring, so it counts in the ring. So I'm going to start there. 1, 2, 3, 4. We also know the carbonyl carbon counts in the ring, so 5. So let's go ahead and make a 5-membered ring. We know the oxygen is here, and no, it doesn't matter where you put the oxygen. I just like to always put it in that spot. So we have this guy, and let me go ahead and number 1, 2, 3, 4, 5. So now I want you guys to tell me what substituents I have to add and where, please. Methyl on 2, perfect. A chlorine on 5, perfect. And one more. Yes, an oxygen on 5. Perfect. And once we've reached this point, I want to kind of address another message that I got in the chat. So someone said, would the nitrogen work as a reducing species? And I'm actually really glad you brought it up, because that's a really good concept to remember from chapters 11 and 12. The reason that it would not work as a reducing species in this case is because we have this acidic hydrogen. So it could have also attacked here and reduced our acid halide. However, it's more favorable for it to just steal this hydrogen and act like a base than it is for the hydride ion to attack the carbonyl and act as a nucleophile. So if it's easier to grab a hydrogen because it's acidic, it's going to prefer to do that. Does that sort of kind of make sense? I hope. Okay, so let's move this over a teeny tiny bit. So now at this point, we have a negative charge on our oxygen. So what are we going to do to fix that bad boy? We're going to make a carbonyl, aka reform our double bond. Perfect. And so at this point, we can either kick off the chlorine or the oxygen. What do we prefer to do? Kick off chlorine, cool. And why do we prefer chlorine over oxygen? It's a better leaving group, true. There's one other reason. It's more reactive, that's also true. But I was thinking something even more straightforward. What would happen if we kicked off this guy? We would be going backwards. We would go back to where we started. Exactly. So if we kicked off this one, we would break the ring and we would end up going backwards. So instead, we're going to kick off this dude. And this would be our final product. So the last thing, we are going to name this lovely ring. What would we call it? One person said it, but I want a couple more people to guess. Please. Ooh, okay. So we got a couple people who said gamma and a couple people who said delta. And this happens all the time. People always mix up gamma and delta. So let's review. We got alpha, beta, our upside down fish, and then if we had one more, we would then have our delta, which is like our almost number 8. So this one would be our gamma lactone. This might not make sense to anyone else, but I like to think about it as like we have our sideways fish, we have our B, we have our upside down fish, and then we have our 8. Again, one of those things that I don't know if it'll make sense to anyone else, but ta-da. And then someone said, do we have to include the methyl substituent when naming? So in reality, if you want to do IUPAC naming, yes, you do. But in this case, and for the purposes of this class, we just want to make sure you know the size of the lactone. So don't worry about the substituents. You are welcome. Okay. So let's break a lactone now. And this one is kind of an ugly looking one. So we're going to do it the long way. So first of all, what is going to be our nucleophile? And please be as specific as possible. Awesome. The nitrogen. The nitrogen. So if we have an acid catalyst, what's our first step in the reaction going to be? Protonate, exactly. So the carbonyl is going to snatch that carbon. Excuse me, I got too excited. The carbonyl is going to snatch the hydrogen, give those electrons back to the chlorine, and so now we get plus. So remind me, what's the point of adding a plus charge to our electrophile? It makes the it makes the electrophile more electrophilic. Perfect answer. Cool. So let's attack. And we're going to kick these electrons up. So we get, and I went through that kind of fast, so I'll zoom out. So now we have an OH, and we have our nitrogen attached with the R group, and it's 2 hydrogens. So are we happy here? Nope. So we know that we have a lovely method of getting rid of this plus charge and making the leaving group better. And someone already beat me to my question. We would do an intramolecular proton transfer. So this oxygen is going to steal one of these hydrogens, giving those electrons back. And so we have our OH. Our nitrogen is happy. Now our oxygen has a plus charge. So we have to do what now? Someone actually made a really good suggestion, and then they kind of corrected themselves. So they had said that H2O would be the better leaving group, but then said, oh, I remember that this happened before, and we kind of went through it, and we got a weird answer. So they are exactly right. Last time when we did this, we kind of kicked off both of these options and saw what we would get. And so we realized that we would kick off the OH in order to open the ring. And we prefer for this guy to use its electrons instead of the nitrogen, so then we can make an amide. And then Jared said, as we keep going, the ring gets smaller. And now I can't stop thinking about that. Alrighty. So we have our amine on top, or our amide, on top. And then on the bottom, let's count 1, 2, 3, and I'll count my oxygen 4. So down here, we start with 1, 2, 3, 4. We end up with an OH. So at this point, what's left to do? Dare I say our last step? Deprotonate the carbonyl. Perfect. And as someone pointed out, we have Cl-. So we're going to snatch this guy. And we get our final answer. Ta-da! Now that we've done an example of making a lactone and breaking a lactone with the whole reaction mechanism, we're going to practice one of each, doing it the simple, quick way. So when we want to, well, this isn't even a lactone one. I just put this here for practice, I guess. So what kind of group do we have here? What's the functional group? Ester. Cool. So how do we do this the Rosemary way? What's step 1? What are we going to cut off? Cool. So this is our leaving group, because we're breaking the carbon-oxygen bond. Exactly. So I'll outline that in red. And what's our next step? Now that we've figured out what our leaving group is. Nucleophile, exactly. And someone said it's the oxygen, so perfect answer. And then last but not least, what are we going to do? Remove a hydrogen. Perfect. So let's get rid of that guy. So we get bam. And this oxygen is attached to a carbon that has 2 other carbon chains, aka secondary. So what kind of functional group did we make? An ester. Sweet. So do we have a name for this reaction? Okay, cool. Okay, yes. So we would call this a S or N esterification for sure. And more specifically, since we went from ester to ester, we would call that a trans esterification. Perfect answer, guys. Alrighty. So for this last one, please tell me which bond we are going to break. Carbon, oxygen, cool, which means this is our leaving group. So who's our nucleophile? Nitrogen. And what's our last step? Take away one of the hydrogens. Perfect. So I'm just going to get rid of the number 2 here. So this time it's super important to keep track of everything. So I'm going to go ahead and number this chain. So 1, 2, 3, 4, 5. So I'm going to make a 5 carbon chain. 1, 2, 3, 4, 5. And you guys tell me what goes where. So first of all, what carbon did our nucleophile attach to? Carbon 1. Perfect. So let's add nitrogen. And where is our benzene ring going to be? What 2 carbons is it attached to? 4 and 5, sweet. So I'm going to erase these numbers and go ahead and add ta-da. And what is the last thing? What's the last substituent we got to add here? Our oxygen, cool. And we are going to add that on carbon 5. And we know that we're not just going to end up with an O. So what functional group will this turn into? An OH, aka an alcohol. Perfect. And then someone said, just to make sure, this is the simplified way of breaking a lactone. Exactly. So we are going to treat this just like any other chapter 17 reaction. And I forgot to draw this, so that's my bad, but there will be a hydrogen on the nitrogen. Any questions? I will go up a little bit so you guys can see both, just in case. No? Alrighty. So the last one, we're going to make a lactone, excuse me. And so for this one, what's our leaving group? One person said it, but I want a few more people, please. Just so I know I'm not going too fast or anything. Cool, yes. So this bond is what we're going to break. So this guy will be our leaving group. Sweet. So then who is our nucleophile? Oxygen, sweet. And so last step would be remove the hydrogen. And someone actually made a really, and then someone also said count. Perfect, you know me too well. But before we do that, someone said that HCl could be our nucleophile. And the only reason we can't do that, because normally anything with a negative charge can be a nucleophile, but why wouldn't it want to be a nucleophile in this case? Let's pretend we didn't cross it out. Someone said sterics. Yes, that's part of the answer. But there's another, I guess, better way to put it. Or not better, but like more straightforward. This hydrogen is super what? So it's an A. Acidic. Cool. So that means the chlorine will want to act like a base because of sterics. It's less sterically hindered. It's more favorable. So it would rather act as a base and steal this acidic hydrogen than attack. Another reason is if we attacked, we would end up making the same exact product. So that would essentially be a no reaction kind of thing. The third thing, can we ever make acid halides through a nucleophilic acyl substitution? No. Perfect. So that would be another reason why that wouldn't work. But that's a great kind of idea. I'm glad someone mentioned it. So, as someone said, we were going to count. I don't know why I developed an accent for like 0.2 seconds. 1, 2, 3, 4, 5, 6. Cool. So before I draw it, if it's going to be 6-membered, what kind of lactone is that going to be? Delta. Perfect. All right. So let's go ahead and draw a delta lactone. That's so ugly, but I'm not going to fix it. What substituent must I add? Methyl? Yes. And where is that methyl going to go? On carbon 3. Perfect. And you guys already told me, but I'll write it down for you. This is a delta lactone, aka delta lactone. So I'll zoom out so you guys can see the whole page. And everything that we just did, the same exact rules apply for lactams. All it would be is switching a nitrogen and an oxygen around, but it would be the same rules.
I have a random question.
Yes, those are my favorite.
Well, it's not really random, but it doesn't, whatever. So is the test going to be like majority the new information or majority like the previous information, or like half and half?
So that's a great question. I can't answer that with like 100% certainty yet because Dr. West hasn't given us the breakdown yet. But from my experience in past semesters, it's usually fairly evenly spaced out. There might be like 2 or 3 more questions for chapter 17 and 18 than let's say 11. And he does like chapter 9 a lot, so there might be like 1 or 2 extra questions in chapter 9. But for the most part, he does it pretty evenly. But again, I will wait until he gives you guys a breakdown or us a breakdown before I like give an official say. Alrighty, that's a great question though. So let's switch gears and jump into chapter 18 for the last few minutes. Or 12 minutes, I don't know if that's a few, but whatever. So we're going to do a thing called tautomerization. And I for sure did not give myself enough room, so I'm going to add a page. Yeah, sure, I spelled that right. All right, so we're going to do a tautomerization. And this is something that's kind of similar to resonance, but I don't want you guys to mix those up because that is a really common mistake that people tend to make with this chapter. So tautomerization and resonance seem similar, but they are not the same thing. As we've done, why'd you do that? In the past few chapters, we're going to start out with a ketone. And I want you guys to remind me, what is the alpha position? So someone said, is it the carbonyl carbon? Not exactly, but you're very, very close. Yes, it is the first carbon next to the carbonyl. So it is the carbon directly adjacent to the carbonyl. So if we zoom in, this one and this one will be our alpha carbons. And then this one will be beta, so on and so forth. We don't really care about the beta. So what is something kind of special about this alpha carbon? I mentioned it very briefly when we were talking about one special reaction in chapter 16 that dealt with the alpha carbon. Does anyone happen to remember? It's very acidic. Awesome. And someone else said that it can form a double bond. And yeah, that's the same concept. It essentially means that it's super acidic and it can be removed. So, or the hydrogen, not the carbon. So let me move this little alpha and draw out our hydrogens. And I'm actually going to draw them in two different colors. So we have the purple alpha carbon and the blue one. So these are both super acidic, but which side do we think is going to be even more favorable to take or to steal? That was so quick. They said the right side. Yes, you're totally right, and I'm so impressed with how fast that was. So why would we prefer to take a blue hydrogen rather than a purple hydrogen? Because it makes a more stable double bond. Exactly. AKA it's a more substituted double bond. Perfect. So those are all the concepts we need right now. Very perfect review. You guys did great. So I'm going to give us Cl2 and H2O. Actually, I'll give us H3O plus, just so it's a better acid. So we're going to do this one time in acid and then one time for base, catalyzed. So in an acid catalyzed reaction, what are we going to do in the first step? Protonate, exactly. So bam, bam, cool. And then, yes, apparently this is the fourth question on the SI sheet. Yes. So after we protonate, I'm not going to color code the hydrogens again because I'm lazy. We said that these hydrogens would be the more acidic or the best ones to remove. So what do we have here that could remove a hydrogen? I'm sorry for the background noise. My sister is, I don't know what. So Cl, okay, cool. Yes, Cl usually can remove a hydrogen, but in this case, do we have Cl minus? No. So do we have something else that could potentially steal a hydrogen? Yes, so we have H2O, which is not the best base, but it's not the worst. So we are going to go ahead and steal this hydrogen. And at this point, we give those electrons back to the carbon. And we make a negative charge. And we have our plus charge here. Are we good so far with what we did? And actually, forget that I added this for a second, just because I don't want to give you guys too much since we only have a few more minutes left. So take out the Cl2 and let's only work with our acid. I hope that wasn't confusing. We just removed the Cl2. Okay, so does anyone have any idea what we could do at this point? We have a plus charge and we have a minus charge. How do you guys think we could possibly stabilize that? Form a double bond. Perfect. So I'm going to draw my arrow in blue just because. So if I bring my double bond up here and we move this double bond up, we end up forming a double bond here and an OH. So this is it for our tautomerization in acid catalyst. So essentially, we started out with a regular old ketone. We ended up removing this hydrogen, the alpha hydrogen. We got a negative charge here on the carbon. We brought those electrons up and kicked up the double bond of the carbonyl. And so this step is actually, it has a special name that we've used a bunch of times before. If all we're doing is moving around the electrons, what did we do? Starts with an R. Resonance, cool. So I'm going to make this into a resonance arrow. And then someone asked, would we always start with a ketone? You can also do this with an aldehyde, but for the purposes of this class, we're just going to work with ketones, just because that's simpler. Alrighty, so we already know that this is a ketone. Does anyone have any idea what this thing would be called? The enol, sweet. So we have our enol. And the cool thing that you guys have to remember is that since these are resonance structures, they are the same molecule and they are both the enol. So both of these are the enol. I'll move this in the middle just so it's more obvious. And I'll zoom out a little bit. Someone said, do we put the double bond in the more stable alpha carbon? Yes, we do. So we are always going to choose the more stable alpha position and steal the hydrogen from there, so then we can make the more substituted double bond. You are correct. So we have one more thing to name here. Does anyone have any idea what the intermediate for an for this tautomerization would be? The enolate. Cool. So what is going to be our enolate? This should be kind of straightforward. I'm not trying to trick you, I promise. The second step, cool. It's the intermediate. So this is kind of a weird looking version of the enolate because it has a plus charge, but the enolate is going to be the intermediate between the ketone and the enol. So really quick, we are going to do the same thing in base. And it's the same reaction, just with a base catalyst. So it should go a little bit quicker. So if we have OH minus, what is our first step going to be? It's a little bit different than the ones we've done before because now we don't have a nucleophile to deprotonate. What do you guys think the OH can do? Also, I'm going to send the attendance sheet one more time because I know a couple people added. Yes, it's going to take the alpha hydrogen, and which one is better, blue or purple? Blue, sweet. So we take this, give these electrons here. We get our negative charge, right? And so now what can we do with this negative charge? Yep. We're going to throw it up here, bring these electrons up here. That's going to be our resonance step. And now we get this. And our last step would be what? Protonate, yes. So we protonate with our OH. So we steal that hydrogen, give those electrons back, and now we get the enol again. So the difference here is just that we get to see the enolate better. So we have our ketone, we have our enol, but our intermediate here that has the negative charge is going to be our what? You guys already said it. Our enolate, perfect. So just to distinguish it from everything else, we're going to put that in green. And these are going to be the two resonance structures of our enolate intermediate. So we know that these two forms of the enol are resonance structures. We know that these two forms of the enolate are resonance structures. But what is the relationship between the ketone and the enol? What do you guys think? If you don't know, that's okay. Hint, it has to do with the name of the reaction. Tautomers, exactly. So we have our ketone, enol, tautomers. Or we can also call it a ketone-enol tautomer pair. So I know we went a couple minutes over, so I apologize. But essentially, a tautomer is. Sorry, I got distracted by the chat. Essentially, tautomers are a pair of structures which readily interconvert in acid or base. And I'll say that again. The definition of a tautomer is a pair of molecules that rapidly interconvert in acid or base. And then someone said, so are the two enols from the acid catalyzed reaction tautomers? No. So these two are resonance structures of one another, but the enol to the ketone is a pair of tautomers. And the reason they're tautomers is because we took this hydrogen and through a reaction, we moved it up here. So in resonance, we don't move actual atoms around. All we do is move electrons. But in this case, we took a hydrogen and we moved it up here. Same as here, we took that hydrogen and we moved it up here. Make sense-ish? Yes, so the tautomer pair is the ketone and the enol. And if anyone needs, I can say what the definition of a tautomer is. Again, if you guys want, just let me know. And again, I'm sorry we went 5 minutes over time. I just thought I would do this faster, but I was kind of slow. So a tautomer is a pair of molecules that readily interconvert in acid or base. And you know what? I'm just going to write it. Ta-da. My handwriting is terrible, but that's okay. So that is all I have for you guys today. I apologize for going over, but you guys are awesome for sticking around. I'll send the attendance sheet one more time, just in case you didn't get a chance to sign in. I'll, as always, stay on for a little bit in case anyone has any questions. If not, have a great day, and I will see you on Wednesday. Bye-bye. You know what? Don't make fun of my terrible writing. And yes, someone asked me to go back to the chapter 17 handout, so I will do that. Ta-da. So I can also zoom in to the first one. Any questions or just wanted to see it? Bye! Thanks for coming, Jared. You're very welcome.